Hi everyone, I'm Zijian Wang from the University of Queensland. Today I'm going to introduce you Learning to Diversify for Single Domain Generalization. This work is collaborated with Yadan, Ruihong, Huang, and Mahsa Baktashmotlagh. So I will start with introducing the motivation of our work. The remarkable success of modern machine learning model is built on the IID assumption, where the training and test dataset are from the similar distribution. However, this assumption is commonly violated by various factors, such as change of illuminations, object appearance, or background. When such difference exists between the training and test dataset, the performance of the machine learning model will be significantly degraded. Domain generalization is therefore proposed to enhance the generalization of the model on the unseen domain. Well, domain generalization enhances the generalizability of the model on the unseen domain. It strictly relies on the availability of multiple source domains. Collecting a set of distinct domains is a non-trivial process. As such, it is more realistic to enhance the domain, the generalization ability of a model from one single domain. Recently, single DG method learns to add adversarial noise on the source image. However, as we can see from this example here, the generated image are not sufficiently diverse to cover the target distributions. So this is the overview of our proposed method. To achieve the goal of diversified source domain, we design a style complement module followed by the backbone class and classifier. We will break down the framework and discuss each part in the following slides. So the objective of the style complement module is trying to generate images that are diversified from the original image. The source image first passes through the convolutional layer, and then the style modification will change the intermediate statistics. And the result will be passed through the transpose convolutional layer to generate the output. And then we are combining the output from different style modifications to have the final generated images. The module will be trained by a mutual information minimization objective, where we're reducing the shared information of the latent variables by optimizing the upper bound of mutual information. Meanwhile, we need to ensure that the generated image contains similar semantic information to avoid the trivial solution, so that we add in the conditional maximum mean discrepancy as a regularization term to keep the style complement module from generating trivial images. Despite generating diverse images, the semantically similar image should be close in the latent space to get the domain invariant representation. To achieve this goal, instead of directly optimize the lower bound of mutual information, we're trying to minimize the supervised contrastive loss. We employ a two-step optimization. In the mutual information maximization step, we are trying to update parameters in the backbone and classifier. Well, in the mutual information minimization step, we're trying to update the parameters in the style complement module. We conduct single domain generalization experiments on the DG's dataset. As we can see from this table, our method can outperform the second best method by a large margin. Meanwhile, our method achieved the largest improvement on exhibition domain, which can be considered as the largest domain shift over the source domain MNIST. We visualize the extracted unseen target feature of different methods. Different color indicates different semantic class. So from the figure, we can clearly see that our method has the best classified separation. Meanwhile, we can also observe that the baseline method has different clusters inside one class, while our method does not. This indicates our method can achieve a better domain invariant representation. Also, there is an experiment. We follow the traditional DG setting where we are leaving one domain out as the testing domain. So from the result, we can see that our method achieved the best performance. And also in the meantime, we argue that the domain identifier is not mandatory to train a domain generalizable classifier. So this is our generated image. Thank you.